For decades, astrophysicists have agreed that the universe is expanding. But right now, cosmology is paralyzed by a problem it cannot solve. Depending on how we measure it, the universe is expanding at two entirely different speeds. This visualization shows the divide. If we measure the early universe, the data shows space expanding at a rate of 67 kilometers per second per megaparsec. But measure the late universe, the space closer to us, and that rate jumps to 73. Initially, researchers assumed our tools were slightly miscalibrated, but recent data from the James Webb Space Telescope eliminated that possibility. The instruments are flawless. Both numbers are mathematically correct. Astronomy has encountered this kind of immovable contradiction before. In the 1800s, scientists mapped the orbit of Mercury and found it violated Newtonian physics. For decades, they assumed their calculations were simply missing a hidden variable. That orbital anomaly forced a choice: ignore the data or acknowledge that classical physics had reached its limit. Albert Einstein used that specific discrepancy to prove the necessity of general relativity. The Hubble tension points to the same crossroads. This 5 sigma discrepancy suggests that our current model of the universe is leaving a massive physical layer unaccounted for. To understand how one universe can produce two different expansion rates, imagine you are standing in the middle of a dark, empty room. If we spray water at you, your body blocks the flow. We can map your physical, localized structure by looking at the dry silhouette left behind. You act as a solid barrier. Now suppose we shine a flashlight on you instead. The light passes by you and casts a shadow on the wall. We are now measuring your distributed, informational imprint, a shape without any physical substance. You never changed. Your biology remained exactly the same. The only thing that changed was the medium we used to observe you. Reality functions in the exact same way. It exists simultaneously as localized physical structure and as a distributed information field. This exact dynamic scales up to modern astrophysics. When cosmologists measure the late universe using supernovae, they are spraying the water. They are measuring the heavy thermodynamic bodies making up the physical cosmos. As these structures form, that work naturally drives the local expansion rate to 73. This heat map shows the cosmic microwave background, the oldest light in the universe. Measuring this is like shining the flashlight. It captures the universe's pure information field before heavy matter formed, so its expansion rate sits lower at exactly 67. We are seeing the results of two distinct physical states, structure and information, being sampled by the same instruments at different points in cosmic time. The tension exists because standard cosmology expects these two regimes to share a single, unified expansion history, but the data suggests they are moving at different speeds. If both numbers are correct, the universe operates in two modes simultaneously. We call this the chrysalis phase, where the early wave field and late matter field overlap like a Mobius strip. Here, they require a mediator, the buffer, an interface processing wave potential into localized matter. Because this buffer consumes thermodynamic energy to convert information into structure, a measurable gap between the 67 and 73 expansion rates is structurally required for the universe to function. The Hubble tension is the visible signature of this cosmic engine in motion. It marks the exact space where the universe translates pure information into physical reality.